Hello everyone, welcome to our first lecture on chemistry A2 levels. Today we'll be discussing lattice energy. So let's get straight into it. What is lattice energy? Lattice energy is basically the enthalpy change or the energy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. Right? So there's a couple of key terms in the definition. The first thing is that it's supposed to be only 1 mole of an ionic compound. Then secondly, it's supposed to be formed from its gaseous ions. So ions can exist in various states, but in the definition we are particularly talking about gaseous ions and under standard conditions. To recap, what is standard conditions? Standard conditions are temperature has to be 298 Kelvin, which is basically the room temperature, and pressure has to be 1 atmosphere. Right? So let's take an example of this. So if you want 1 mole of an ionic compound, which means let's say NaCl, the ionic compound, right? Now, only 1 mole of an ionic compound has to be produced from its gaseous ions. Now, NaCl consists of 2 ions, right? It has Na plus and Cl minus. So, it's formed from Na plus and Cl minus, and both of them has to be gaseous. And this reaction takes place in standard conditions. So, we can formally write this as like this: Na plus in gaseous form plus Cl minus in gaseous form gives you NaCl, which will be a solid. Right? And this will be called enthalpy change, and then you abbreviate this as lattice energy, right? So lattice energy usually is exothermic, and all of the reactions that you will see for lattice energy will be exothermic. So you'll always see a negative sign being written out over here. And the reason why that's the case is because you are forming an ionic compound, and this is a type of bond forming. So you're combining 2 elements to form a bond, and we know that bond making is exothermic and bond breaking is endothermic. So if you are forming a bond, this will be an exothermic reaction. Now, one thing to note down here is that the stronger the lattice energy, the more stronger the ionic bonding is. So for example, let's take NaCl's lattice energy to be negative, let's say 500 kilojoules per mole. And let's say you have another ionic compound. We can take MgCl2. So if you have, let's say, MgCl2, which will be a solid, and it's formed from its gaseous ions, which will be Mg2 plus gas plus 2Cl minus gas as well, forms this. Now, you can predict that because MgCl2 is a stronger ionic compound than NaCl. Why is it stronger? Because Mg has a 2 plus charge and Cl has a negative 1 charge, but the attraction between these two is much more than an attraction between positive 1 and negative 1, right? So this one is a stronger ionic compound, which means that the lattice energy for this one will be much more exothermic than for the sodium chloride. So we can expect maybe negative 800 instead of it being negative 500, and so on. So you can see the trend that stronger the ionic compounds, the more stronger the lattice energy is. Right, let's go on to the next part. Now, before we continue, we have to understand some important definitions. And the best way to understand this topic is to understand really what these enthalpy changes mean, so that when we actually go on to draw the Born-Haber cycles, it will be seamless and easier to work with. Right, so let's start with the meaning of the enthalpy change of atomization. Now, the standard enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atoms is formed from its elements under standard conditions. So again, we have some key terms here. The first one is that it's supposed to be 1 mole and then of gaseous atoms, right? And it's supposed to be under standard conditions. Now, just a basic example of this will be that let's say you have sodium, right? You have sodium as a solid. The enthalpy change of atomization of sodium will be that you are forming the gaseous atoms and 1 mole of it, so sodium gas, right? And you can abbreviate this like this, delta H hat. And this value will always be positive. And why is that? Because whenever you are doing atomization, you are actually giving this energy. You are supplying this energy to convert it from a solid to a gas. because you are breaking the bonds within the sodium metal. You are trying to separate the sodium metal by giving it energy, right? So then it becomes a gas. So bonds, this is bonds breaking and it will always be exothermic. Another example of standard enthalpy change of atomization will be, for example, chlorine. Now, for example, chlorine exists as a gas, right, in its original state. So usually we have Cl2, which is a gas. Now you might ask, how can this have an atomization? Now, remember here we say that it's supposed to be 1 mole of gaseous atoms. This is Cl2. Cl2 is a molecule. Why is it a molecule? Because a molecule contains 2 atoms bonded together. So you can also have Cl2 becoming Cl as a gas. So this is an atom now, right? And initially it was a molecule. But to balance the equation, we have to keep half over here. So that's both sides have 1 chlorine. And again, this will be enthalpy change of atomization. And it will also have a positive value because you're breaking the bond in the chlorine molecule to form this atom. Right, let's go on to the next thing, which is the standard enthalpy change of hydration. Now, what does this mean? This is just the enthalpy change when 1 mole of gaseous ions is dissolved in excess water to form an infinitely dilute solution. And this is always exothermic. So what does this mean? For example, you have NaCl, right? And you have NaCl and you want to dissolve this in water. Now we know that NaCl consists of Na plus and Cl minus ions. And when it dissolves in water, it's going to become NaCl aqueous, whereby there will be attractions between NaCl and the H2O, which will be the water molecules. So basically the energy change required for these ions to dissolve in water. What's the energy released when they dissolve in water? That's basically what enthalpy change of hydration is. And you can understand why it's exothermic. It's because you're forming these bonds between the ions and the water molecules. There's some sort of permanent dipole-dipole interactions which are taking place. So this energy release is what makes the equation exothermic, right? So how is the equation written? It's written like this. In the original NaCl, you have Na plus and Cl minus. So you can start with the Na plus as the reactant. And remember, it's gaseous. Okay, so you have to keep a gas here. And when it dissolves in water, you form Na plus aqueous. Right? That's it. That's basically the equation. Some others write plus 8 over here. You can write this, you can write this, it's up to you. But this is what it essentially is. You are going from Na plus to Na plus aqueous. And the delta H for this will be exothermic. So you'll always expect a negative value. Now, one more thing before we finish this is, what does an infinitely dilute solution mean and why do they write this? So this was something that I used to have trouble in when I was studying this, and the reason for this is that if you don't have a dilute solution and you have a concentrated solution, let's say this is your water and you keep the NaCl over here. The issue with this is that the NaCl ions will be close together, right? So you might have Na plus here and Cl minus over here. Now you know that if two ions are close to each other and they are oppositely charged, they attract, and when they attract, the attraction between them will release some sort of energy. So there'll be extra energy released because of this attraction. And you won't be able to measure the enthalpy change of hydration accurately. Why is that? Because hydration just involves the change from Na plus gas to Na plus aqueous. But if it's not a dilute solution, this hydration value will also include the energy changes between these ions, which were either attracted or repelled, right? Because you can even have a Cl minus ion here and a Cl minus ion here, so they repel. So there's energy changes which take place because of these ion attractions. So if you have a dilute solution, the ions are far from each other, and so it's not affected by these energy changes, right? So I hope that makes it clear why they use this. Okay, now lastly, we'll talk about the enthalpy change of solution. This is the enthalpy change when 1 mole of an ionic solid dissolves in excess water to form an infinitely dilute solution. So you can see very similar definitions between hydration and solution. The difference is that this one is gaseous ions as a reactant and this one is ionic solid. Another difference is that the solution enthalpy change of solution can either be exothermic or it can be endothermic. Now, why is that? For example, let's take again NaCl, our favorite ionic compound. If this one is dissolved in water, then there are two energy changes taking place. The first one is that for this to dissolve in water, it becomes NaCl aqueous, right? So you have to break this solid structure. You have to break the ionic lattice, which was in NaCl. This is bond breaking, right? So this one is bond breaking. And then again, this NaCl forms uh, permanent dipole-dipole attractions with this water. And so it's forming the bonds. So this is bond forming. Now, if the bond breaking is more than the bond forming, then it's endothermic. But if it's the other way around, then it's exothermic. So that's why there is two different possibilities here. But for the hydration, you didn't have a solid initially. You just had a gas. So you had Na plus as a gas, right? So there is nothing to break over here. A gas is the smallest possible state. So that's why this was always exothermic. But for solution, you can either have exothermic or endothermic. Now, another important thing to note here is that the more exothermic the enthalpy change of solution is, the more soluble it is. So for example, let's say you have NaCl and its enthalpy change of solution is maybe negative 200, right? And if you have something more soluble than NaCl, let's say NaNO3, and it has a value of negative 300, if it's more exothermic, it basically means that sodium nitrate is much more soluble than NaCl. Okay, let's look at the next part, which is electron affinities. And this concept is new, but it's very similar to ionization energy. It's just that it's the exact opposite of it. So, and the first electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous 1 minus ions under standard conditions. If you remember from your AS level, ionization energy was exactly the opposite. It was when 1 mole of electrons is removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1 positive ions. And this is literally the opposite of this. So let's take an example of a chlorine molecule, which will be in gaseous state, and plus an electron, because 1 mole of electron is added, and it forms a chlorine 1 minus ion, right, which will be in gaseous state as well. Now, the enthalpy change for this one will be negative, and it's an exothermic reaction. Why is that? Because you're adding an electron to a chlorine atom. This is, you are trying to combine two things, and usually when two things combine like this, they release energy. It's opposite to ionization energy. Remember, in ionization energy, the outermost shell removes one electron of it, so you have to give it energy to remove it. But this time you're doing opposite of it. So instead, the electron is combining over here, right? So this is an exothermic reaction. Now, an important distinction to make here is that the first electron affinity will always be exothermic, but the subsequent electron affinities will be endothermic. So, for example, the second electron affinity, the third one, the fourth one, etc., all of them will be endothermic, but the first one will be exothermic. I've already explained why the first one is exothermic. Now, why are the second, third, etc., all of them endothermic? The reason for that is because, let's say from our earlier example, you formed a chlorine minus ion, right? Now, if this chlorine minus ion has a negative charge here, and you're trying to add another electron to this thing, this is negative, and then this is negative. So both of them will try to repel each other. So you have to supply some energy to force the electron to go into this chlorine. And that's the reason why the subsequent electron affinities are endothermic. Now lastly, you have to be aware of the trend in electron affinities. And the trend is that it decreases down the group. Why is that? Is because even though the nuclear charge is increasing, the shielding effect also increases. Therefore, there is less attraction between the nucleus and the incoming electron. For example, let's take group 7, right? It has fluorine, chlorine, bromine. As you're going down the group, the number of shells are increasing. So chlorine has more shells than fluorine, and bromine has more shells than chlorine. So you can see that the shielding effect is much more, right, as you go down the group. If the shielding effect increases, the nucleus, which is in the middle, so let's take this as fluorine. This is the nucleus in the middle. And then it's trying to attract this electron over here. This is positive, the nucleus. The attraction for this one will be much more than an attraction for someone who has much more shells, right? So if the positive charge is further away from the electron, it becomes harder to attract this compared to this one. Okay, so as you go down the group, electron affinity decreases. Right, now the final thing that you have to know before we actually start to draw the Born-Haber cycles is a couple of definitions. So just to recap, ionization energy, what it means is that it's the energy needed to remove one electron from each atom in 1 mole of atoms to form 1 mole of gaseous 1 plus ions. This is basically the same thing we have covered in AS level, and we will use ionization energy while drawing Born-Haber cycles. So it's quite important to recall this. Just to recap, the equation for this was, let's say you have sodium and you want to remove an electron from this. Now remember, this one has to be in gas, right? This charge. Now you want to remove an electron from this, so it's going to become an A plus in gas plus 1 electron, right? Which is also in gas. So that's the basic recap of ionization energy. And lastly, you have to know what enthalpy change of formation is. So again, the same definition of Aristotle. It's the enthalpy change when 1 mole of a compound is formed from its elements in its standard states under standard conditions. So again, we can take, let's say, MgCl2, right, which is a solid. So the enthalpy change of formation, if you want to write the equation of it, will be, what are the elements in MgCl2? You have Mg and you have Cl2, right? They combine to form MgCl2. And this one is a solid because we need to keep in their standard states, and chlorine is a gas and magnesium is a solid.